Hello everyone, welcome to the BiyokimyaVET channel. I'm here with the topic titled Carbon Atom. Do not forget to start by liking the video, my friends. I wish it to be useful. Let's start. And here is the contents of this topic. We'll talk about the carbon atom, its hybridization, and there are three types of hybridization, which the one is sp3, then sp2, and we will talk about sp hybridization. And the following titles are conjugated double bonds, aromatic compounds, and carbonyl group. Carbon atom, the atom at the heart of the organic chemistry, and we also define organic chemistry as the chemistry of carbon atom. And the carbon compound as a common feature consists of carbon, and it's a must, and also hydrogen. They are highly hydrogenated molecules, and as well as they contain heteroatoms, and they form variables, different maybe the thousands of different molecules by combining carbons and hydrogens. According to the bond type and molecular structure, carbon compounds can be divided into two main groups. The one is saturated carbon compounds, such as alkanes, and the carbon compounds having only carbon-carbon single bonds, and the unsaturated carbon compounds, such as alkenes, or the compounds carrying at least one carbon-carbon double bond. The determinants of the physical and chemical properties of organic compounds are the binding styles of the compounds and the binding forms. So the type of bond and its form, either single bond or triple bond, is very critical for any organic compound, and it is determined by hybridization of carbon. And Linus Carl Pauling, the father of carbon atom, I can say it's father of carbon atom. And Linus Carl Pauling was an American chemist, a biochemist, a chemical engineer, an educator. And he published more than 1,200 articles and books, including about 850 on scientific topics. And the New Scientist named him one of the 20 greatest scientists of all time, and as of 2000, he was ranked the 16th most important scientist in history. And for his scientific work, Pauling was awarded the Nobel Prize in Chemistry in 1954, and he was awarded the Nobel Peace Prize in 1962 for the peace activism. He was also an activist. And as I said, more than 1,200 articles and books were written by Linus Carl Pauling. He is one of the only 5 people to have won more than one Nobel Prize, and the others being Marie Curie, John Bardeen, Frederick Sanger, and Carl Berry Sharpless. Among them, he is the only person to have received 2 Nobel Prizes that were not shared, and one of only 2 people to have received Nobel Prize in different fields, and the other being Marie Curie. Pauling was one of the founders of quantum chemistry and molecular biology. His contributions to chemical bond theory include the concept of orbital hybridization and the first accurate scale of electronegativity of elements. Pauling also worked on the structure of biological molecules and showed the importance of the alpha helix and beta sheet in protein secondary structure. Pauling's approach combined the methods and results of X-ray crystallography, molecular modeling, and quantum chemistry. Pauling's discoveries inspired the work of Rosalind Franklin, James Watson, Francis Crick, and Maurice Wilkins on the structure of DNA, which made it possible for geneticists to crack the DNA code of all organisms. And here is one of the notable articles published by Pauling in 1932, The Nature of Chemical Bond Transition from One Extreme Bond Type to Another, published in Journal of American Chemical Society. Yes, after a brief information about the father of carbon atom, it's time to start hybridization. Yes, hybridization. Actually, we can say revise the word as the father of hybridization for Linus Pauling. Two hydrogen atoms share each of their electrons to form the hydrogen gas. Thus, the 1s orbital on one hydrogen overlaps with the 1s orbital on the other hydrogen to form a bond that concentrates electron density between two nuclei. And this type of bond called the sigma bond. And shortly, sigma bond is a type of single bond. And for all single bonds, we call them sigma bonds. So a sigma bond concentrates electron density on the axis that joins two nuclei. And all single bonds are sigma bonds. And the sigma bond is cylindrically symmetrical because the electrons forming the bond are distributed symmetrically upon an imaginary line connecting the two nuclei. Carbon has two core electrons plus four valence electrons. This lowest energy arrangement of electrons for an atom is called its ground state. And to fill atomic orbitals in the most stable arrangement, electrons are placed in the orbitals of lowest energy. And for carbon, this places 2 in the 2s orbital and 1 each in two 2p orbitals. And here is the electron configuration of carbon: 1s2, 2s2, and 2p2. And accordingly, carbon should form only two bonds located at the outside, only two electrons, because it has only 2 ampere valence electrons. And the CH2, which is called the methylene or methane or the carbene, should be a stable molecule. In reality, however, methylene is a highly reactive species that cannot be isolated under typical laboratory conditions. In methylene, carbon would not have an octet of electrons. Thus, methylene is an organic compound with the chemical formula CH2, and it's a colorless gas that fluoresces in the mid-infrared range and only persists in deletion or as an adduct. And methylene is the simplest carbene. It is usually detected only at very low temperatures or as a short-lived intermediate in chemical reactions. There is a second possibility. Formation of an electron from a 2s orbital to a vacant 2p orbital would form 4 unpaired electrons for bonding. And here is in the picture you see the ground state of carbon. And 1s electrons are small and not shown, the 1s electrons. They are not involved in bonding. And two paired 2s electrons are spherical and are symbolized with two arrows, the 2s orbitals. And there are two unpaired 2p x and y 2p orbitals that align on the x and y axis, and we call them 2px, 2py, and 2pz. As the carbon atom nears another atom such as hydrogen, one of the electrons in the 2s orbitals get pulled into a higher energy orbital, In this case, it goes into the unfilled 2pz orbital. This electron, 2pz orbital. The process requires energy. This process requires energy because it moves an electron to a higher energy orbital. This higher energy electron configuration is called an electronically excited state. Carbon do not use pure s and pure p orbitals in forming bonds. Instead, atoms use a set of new orbitals called hybrid orbitals. And hybridization is the combination of two or more atomic orbitals to form the same number of hybrid orbitals, each having the same shape and energy. And there are three types of hybridization: sp3, sp2, and sp. Let's start with the sp3 hybridization of carbon atom. The configuration of the carbon atom is given as 1s2, 2s2, and 2p2, and the upper numbers give the number of electrons in the orbitals. Hybridization of 1 2s orbital and 3 2p orbitals for carbon forms 4 hybrid orbitals. And also this tells us a carbon atom in this state can form 4 bonds. And in general, in each hybridization type, carbon can form 4 bonds, either 4 single bonds, or 1 single, 2 single, 1 double, or 2 double, or 1 single, 1 triple. These new hybrid orbitals are intermediate in energy between the 2s and 2p orbitals. And in the formation of a bond, the number of electrons in these orbitals and many other properties are changed or hybridized. And these hybrid orbitals are called sp3 hybrids because 1s orbital and 3p orbitals are hybridized to form 4 sp3 hybrid orbitals. Thus, in this hybrid model or in this hybridization state, carbon will form 4 single bonds with other atoms. The sp3 position is formed on the unbound carbon atom in the s2p2 position, and 2s orbital and 2p orbitals merge and sp3 hybrid orbitals are formed. And each of these 4 hybrid orbitals has 1 electron each. The valence electrons of the carbon atom are equally distributed in the orbitals with exactly the same structure, and the long axes of the hybridized orbitals show the 4 corners of an equilateral triangular pyramid. And the carbon atom is located at the intersection of the axes. The 4 hybrid orbitals form 4 equivalent bonds. And each bond, as in methane, a component of natural gas, is formed by overlap of its sp3 hybrid orbital of carbon with a 1s orbital of hydrogen. And these 4 bonds point to the corners of a tetrahedron. And here is the sp3 hybridized carbon, which forms 4 single bonds with 4 hydrogen. And this is we call it a tetrahedron because it forms like a prism, 4-membered prism. An angle between each bonding is approximately 109 decimal degree. And now we can explain the observed bonding in methane, and all 4 carbon hydrogen bonds in methane are sigma bonds. So these bonds are sigma bonds because the electron density is concentrated on the axis joining carbon and hydrogen. The sp3 hybrid form of the carbon atom is called the tetrahedral model or tetrahedron. We have been discussing orbitals so far. This alone provides atoms with a great deal of flexibility in associating with other atoms. How these orbitals can combine to form new shapes, giving bonding even greater versatility. This merging is referred to as hybridization, and it's an appropriate term because the final orbital is a hybrid of the original orbitals. Because organic chemistry and biology rely on the carbon atom, we will begin with that element. Carbon's diversity in the formation of complex compounds is only conceivable due to hybridization of its electrons. And one of the hybridization types is the sp3, which we call it the tetrahedral carbon or tetrahedral model or shortly tetrahedron. The carbon forms four bonds which have a bond angle of about 109.5 degree, and this is the tetrahedral carbon. If a carbon atom is attached to four different types of atoms or group of atoms, it is defined as an asymmetric carbon atom, or a chiral carbon, or a stereocenter. And here in this picture, once again, give me a second. Yes. Here in this picture, once again, an electron from the 2s orbital, look at here, 2s orbital, is drawn into unfilled 2pz orbital. And the green 2pz orbital is now visible. The orange dot arrow indicates that it originated in the 2s orbital. And one electron remains in the second s orbital, so the orange sphere remains. Here in the bottom figure, what happens next is that these four electrons combine, which we call it hybridize, and all take on the same shape. And the shape consists of two lobes, one of which is significantly larger than the other. And also we can say the shapes refer a kind of dumbbell, and here is an asymmetric dumbbell. And the shape consists of two lobes, one of which is significantly larger than the other. And the four larger lobes are shown in the right of the image here. The four larger lobes, not the small ones. And the number of orbitals involved is used to name the form. The designation is sp3. sp3. And this refers to the hybridization of 1s orbital and the 3p orbitals. And the exponent in sp3, which means the 3 here, is the number of orbitals. And sp3 orbitals can have 4 to 8 electrons. Notice the 4 unpaired electrons in the sp3 orbital region in the image. If they were all paired, you would have 8 electrons, which means the octet. And the sp3 orbitals forms a tetrahedron. You see the tetrahedron, a pyramid with a triangular base and all equal sides. And the angle formed between the bonds is 109.5 degree. When carbon combines with four other atoms, this is the shape of the molecule. Four atoms here, there, and here, and we call it tetrahedral carbon. And if these four atoms are different from each other, we call it chiral carbon or stereocenter or asymmetric carbon atom. And here you see the methane, the natural gas, and here the carbon is in sp3 hybrid model, and it forms a sigma bonds, which means a single bond with the carbon and hydrogens, 4 single bonds. For example, two sp3 hybridized carbon atoms are bonded together by simple sigma bonds on one valence, while hydrogens can be bonded on the other valence and the ethane is formed. And here is the ethane, and this is a kind of 3D but not a real 3D shape, showing the ethane and the two carbons bond with single bond, and the rest of the bonds are formed with the hydrogens. And count the number of single bonds. There is always 4 single bonds in sp3 hybrid model. And in this way, numerous carbon atoms are bonded to each other and carbon compounds with high molecular weight are formed. And also this is the logic that there are higher rate of diversity in nature in terms of the organic compounds, and this is so critical for the life. Yes, when you see the zigzag lines, focus here, the zigzag lines, those are carbon atoms connecting with the sp3 hybrid electrons, and the angles are 109.5 degrees. Even if the lines are drawn straight like the red ones in the image, there are still 109.5 here and here. And this is a basic representation of organic compounds, and we know at each bending points there is a carbon atom. Thus this means this is the line represents the carbon-carbon single bond, and also don't forget to fill up the number of bonds to 4. This means there are 2 hydrogen atoms at that point, and at the end we have a 1 carbon again and 3 hydrogen bonds to fill up the 4 sigma bonds. And this is the best way to represent, because in real, yes, this is a kind of real illustration of this molecule, and it's not easy to draw that kind of illustration every time. We need more easy way to represent organic molecules. And this is the 3D dimensional Poland stick model, and also actually this is the real tetrahedral angles are representing in this shape. And this is the famous triglyceride, a type of triglyceride, which means a fat, which means a lipid molecule, a deposit and storage lipid molecule for mammals. There are other hybridization patterns also, and one possibility is forming the sp3 hybrid models. This is just one way that 2s and 2p orbitals can hybridize. And there are also other ones, sp2 and sp hybrid models. And the number of orbitals is always conserved in hybridization. That is, a given number of atomic orbitals hybridized to form an equivalent number of hybrid orbitals. And don't forget, whatever the hybridization occur in a carbon atom, there must be always 4 bonds, either 4 single bonds, or 2 single 1 double, or 2 double, or 1 single 1 triple bond. 1 2s orbital and 3 2p orbitals form 4 sp3 hybrid orbitals. And in this hybridization pattern, as I explained in the previous slides, there is a 4 single bonds, which means 4 sigma bonds. 1 2s orbital and 2 tp orbitals form 3 sp2 hybrid orbitals. And in this hybrid orbital, carbon atom forms 3 sigma bonds and 1 pi bond, which means there is a 2 single bond, 1 double bond for the carbon atom. 1 2s orbital and 1 2p orbital form 2 sp hybrid orbitals. And in this form, carbon either forms a 2 double bond or 1 single 1 triple bond. This means there is a 2 sigma bonds and 2 pi bonds in the sp hybrid model. sp2 hybridization. 1 2s orbital and 2 2p orbitals form 3 sp2 hybrid orbitals allowing 1,2p orbital unhybridized. So in sp2 and sp hybridization, there will be always unhybridized orbitals. In sp2, 1,2p orbital is unhybridized. And in this type of hybridization, each carbon is trigonal planar. And in this new structure, the three hybrid orbitals are located in a plane while the third p orbital to pz, which does not participate in hybridization, is perpendicular to this plane. And the second carbon-carbon bond results from side-by-side overlap of the two p orbitals on each carbon. And this new type bond is called a pi bond. Pi bond. And pi bonds are usually weaker and therefore more easily broken than sigma bonds. In the formation of a compound, two carbon atoms hybridize sp2 come side by side and are connected by a simple sigma bond. The two pz orbitals above and below the sigma plane also merge above and below the bond plane. And as the electron clouds of the two pz orbitals intertwine, a new orbital is formed above and below the plane, which is identified as a p orbital to indicate its origin. In sp2 hybridization, a carbon-carbon double bond has two components. A sigma bond formed by end-on overlap of two sp2 hybrid orbitals and the pi bond formed by side-by-side overlap of two 2p orbitals, two 2p unhybridized orbitals. And here's the molecule ethylene, and as you see, the two sp orbitals form a sigma bond, and the unhybridized pz orbitals side by side overlap of two tp orbitals to form the second bond, which is the pi bond. And as I said, there is a trigonal planar, and the bond degree here is approximately 120 degree. So the carbon can form double bonds with the other carbons and as well as with other atoms such as oxygen, other heteroatoms. And the carbon's electrons behave differently when it is surrounded by two hydrogen atoms and one oxygen atom. Because oxygen requires two electrons to create an octet, carbon must share two electrons with oxygen by establishing a double bond. The electron configuration of carbon after one of the two s orbital electrons has been promoted to the 2pz orbital is shown at the top, and free electrons will become hybridized. The free electrons will become hybridized. And here the sp2 implies that it will have one s orbital electron and two p orbital electrons. And this is the configuration. Here we depict the outcome of the three carbon electrons combining to form here the three sp2 orbitals. And take note of how these three sp2 electrons are arranged in a triangle with a 120-degree angle between them. And here is the angle. And this is the hybridization model. This is the sp2 hybrid model. And this will result to form a double bond. And here, double bond is formed between carbon and oxygen. Carbon and oxygen. And here you see in the left image, as you see here, the carbon mixing with two hydrogen atoms and one oxygen atom to generate the formaldehyde. So this is the formaldehyde. And the lowest bond structure is depicted in the top diagram. And the orbitals are shown in the bottom figure as they prepare to bond. It is worth noting that the oxygen electrons went through the identical hybridization process as the carbon electrons. The presence of carbon causes oxygen to hybridize as well. The distinction is that oxygen has 2 more electrons than carbon, here 2 more electrons than carbon, which explains why 2 of the sp2 orbitals are occupied. And this is represented by the 2 black dots, as you see, which represent the 2 paired electrons. And these are known as lone pairs, lone pair of electrons, since they are not employed for bonding. And here you see the 2 sp2 electrons, that were pointing in the same direction overlap and form a connection. And the 2 particle 2p electrons form carbon and oxygen band toward and overlap another, and this also creates a bond, both sigma bond and the p bond. And sigma bonds, by the way, are bonds that overlap directly between 2 atoms. The overlapping region has a spherical form similar to the s orbital. And the sigma bonds are the most powerful. A pi bond is the link generated by overlapping p orbital electrons. Even though the p orbital electrons overlap at the top and the bottom, it still counts as one pi bond. And the double bond sign in the Lewis structure at the top represents the 2 lines, the double bonds. And the sigma bond is represented by one line, like this, one line, and the pi bond is represented by the other. Yes, here's the sigma bond, and the 1 sigma 1 pi bond representing the double bond. And also this is another representing the same molecule as above, but from above I removed the pi bond to emphasize the sp2 bonds. These linkages are plain and form 120-degree angles. And let's continue on sp hybridization, a third type of hybridization. 1 2s orbital and 1 2p orbital form 2 sp hybrid orbitals. And in this hybridization, each carbon is linear, and there's an angle of 180 degree. And in this case, carbon is attached to the 2 other elements. That makes 2 double bonds, or 1 single, 1 triple bond. And one of the bonds form sigma, the others are pi bonds. And here is an example, the acetylene, a hydrocarbon, and the carbons here are in sp3, and as you see, 1 single bond and 1 triple bond occur in acetylene, which is a hydrocarbon compound with the chemical formula C2H2. And this gas has the ability to burn at high temperatures and is used in many industrial applications. And here is another example, the carbon dioxide, and as you see, the carbon forms 2 double bonds. Carbon dioxide is a chemical compound with the chemical formula CO2. It consists of molecules, each having a carbon atom covalently double bonded to 2 oxygen atoms. It exists as a gas at room temperature, and as the current source of carbon in the carbon cycle, atmospheric carbon dioxide is the primary source of carbon for life on Earth. Carbon can connect to an element that requires 3 electrons to reach its octet. Demonstrating its versatility even more, carbon is located at the middle of the hydrogen and nitrogen molecule, and with nitrogen a triple bond is required, as you see here. And hydrogen with single bond, and with nitrogen triple bond. Carbon, like before, promotes one of its 2s electrons to the 2p orbital, as you see. And the other 2s electron, together with one of the p orbital electrons, is then hybridized into an sp orbital. the two electrons in the sp orbital point in opposite directions, one will form a bind with hydrogen, while the other will form a bond with nitrogen. The remaining two bonds will be formed by the two 2p x and y electrons. So these two sps will form the sigma bonds, and the rest, or the unhybridized one, will form the pi bonds. The hydrogen, carbon, and nitrogen atoms are bonded here, and the pink sp electrons aim exactly at the atom with which they will connect. It's worth noting that the electrons in nitrogen hybridize in the same way that the electrons in carbon did. Nitrogen contains one additional electron than carbon, as you see here, which explains why one of nitrogen's sp electron is full, the two dots, and forms a lone pair, a non-bonding pair. The yellow and green lobes represent the same p orbital electrons. They will bend towards each other and overlap. And the sigma bond between the sp electrons has overlapped here, and those bonds are present. The two pairs of p electrons are approaching each other. The p electrons overlap in the following panel. Above and below the sigma bond, the yellow lobes create a single pi bond. To the front and back of the sigma bond, the green lobes form a single pi bond. So, in the Lewis structure depicting the triple bond, one line represents a sigma bond, while the other two lines represent the two pi bonds. The two dots in the non-bonding sp orbital represent the nitrogen atom's lone pair of electrons. And the hydrogen atom also forms a sigma bond with the second sp orbital electron of carbon, because the sp electrons lie on opposite sides of carbon and nitrogen, and there are no lone pairs on carbon to oppose these bonds. The molecule has a linear shape. And thanks to the chemistry learned for these great illustrations. And the good illustration summarizing hybridization of the carbon atom, and here you see the 4 single bonds, which means it's in sp3 model, and here one double bond and the 2 single bonds, and it's an sp2 hybrid model of carbon atom, and here one single bond, one triple bond, which is the sp hybrid model of carbon atom. After understanding of hybridization, let's continue on conjugated double bonds. Many molecules contain 2 or more double bonds and are accordingly called DNs and 3Ns. Here is the ENE. The "en" is a suffix to represent there is a carbon-carbon double bond, and the prefix D and 3 represent the number of double bonds, which means D means 2, 3 means 3, for 4 we use tetra, and 5 penta, and etc. If the double bonds are separated by at least one saturated carbon atom, the two have little effect on one another and react independently. Bonds of this type are said to be isolated or unconjugated double bonds. Conjugation occurs whenever p orbitals can overlap one, 3, or more adjacent atoms. In unconjugated double bonds, the pattern is, for example, one double bond, then a single bond, and then one double bond. And there is a separation between the two double bonds, so they are isolated, and they can react independently. If the double bonds are separated by just a single bond, they are said to be conjugated double bonds. And here the pattern: one double bond, single bond, then double bond, single bond, double bond, single bond. So this is the pattern: single, double, single, double. And conjugated DNs, which means the conjugated carbons having two carbon-carbon double bond, and I mean double bond, single bond, double bond, the single bond. This is at the end, there are the two double bond, and it's conjugated. And the factor that determines their properties is the localization of charge for resonance and hybridization energy. And here is some examples for the conjugated carbon systems, or the conjugated chains. And as you see in this molecule, there may be two parts, and here the part is conjugated system, and this part is an isolated system. And here the carbon 5 is an sp3 hybridized model. And this is another DN and a conjugated DN, actually, this one. A conjugated DN, double, single, double, single, and here an isolated. As you see, the double, then single, single, and double. And here the famous conjugated system, the beta-carotene, a precursor of vitamin A. In aromatic compounds are chemical compounds that contain conjugated planar ring system, which is the benzene. And different structural formulas may be created from the benzene, but with the same valence, generally written in hexagonal, and the circle symbolizes double bonds. And compounds having the benzene ring system are called aromatics or aromatic compounds. And here is the famous benzene ring, a conjugated system. Single bond, double bond, single bond, sorry, let me revise and correct it. Double bond, single bond, double bond, single bond, double bond, and single bond. And I always prefer to draw like this, not the one here showing the circle. The energy content of aromatic system is very low. They have a very stable structure, and all carbon-carbon bond length is the same size due to resonance. And resonance in organic chemistry occurs when electrons are delocalized across multiple double bonds in a molecule. It comes out of most chemical reactions intact, and it is easy to substitute other atoms or groups of atoms instead of hydrogen atoms in its structure. So it can undergo substitution reaction. And the last title of the topic, the famous Carbonyl Group. A carbonyl group is a chemically organic functional group composed of a carbon atom double bonded to an oxygen atom. And here is a carbonyl group, carbon double bonded to oxygen. And the double bonds in alkenes and double bonds in carbonyl groups are very different in terms of reactivity. So in alkenes, the carbon-carbon double bond, and in carbonyl group, we have a carbon double bond oxygen. So they are extremely different in terms of reactivity. And the carbon-carbon double bond is less reactive due to carbon-oxygen double bond electronegativity attributed to the oxygen and its two lone pairs of electrons. Don't forget, the oxygen carries two lone pairs of electrons. And the carbonyl group's properties are directly tied to its electronic structure as well as geometric positioning. For example, the electronegativity of oxygen also polarizes the pi bond, allowing the single bonded substituent connector to become electron withdrawing. And in chemistry, polarity is a separation of electric charge leading to a molecule or its chemical groups having an electric dipole or multipole moment. And the polar molecules interact through dipole-dipole intermolecular forces and hydrogen bonds. Yes, my friends, we are very close to the end of the topic, and here you see the carbonyl group, the carbon-oxygen double bond, and we call the oxygen carbonyl oxygen. The carbon is called the carbonyl carbon. And there is still more to sigma bonds which attach to the X and Y. And depends on the X and Y, there is variable functional groups having the carbonyl group, such as in here, if the Y is hydrogen and the X is an R, a radical group, or a carbon backbone, another carbon backbone here. This is called the aldehyde group. CH bonded to a carbon backbone, CHO. And in here, as you see, the carbonyl carbon forms the two sigma bonds with two identical or maybe different carbon backbones, the R's, which is called the ketone. And here, if there is a hydroxyl group and a backbone of R, it is called carboxylic acid. And there is a good examples because these are a kind of superior functional groups in our body, such as the glucose, for example. Glucose carry an aldehyde group. And fructose, which is the fruit sugar, carries a ketone group. And the amino acids and fatty acids are carboxylic acids. And we will discuss them in the topic of functional groups, the carbonyl functional groups, or the functional groups carrying carbonyl group. And here are the references that you can make a further reading. And the next topic is isomerism and stereochemistry in organic chemistry. And you can visit my website, my Instagram account for more about the biochemistry, clinical biochemistry, and the laboratory world. And please don't forget to subscribe, click on thumbs up, and open notifications for further news. See you in our next topic. Goodbye.